Well, this has been quite a week for the speaker, Burton Richter. Started out on Monday in the White House, receiving the Enrico Fermi Award. I guess it was for 2010, you said, not 2011. It's one of the oldest and most prestigious awards given originally by the Atomic Energy Commission and now by the Department of Energy on behalf of the President of the United States. And now the program announcement, you can read all about his achievements. They just tell you a clue of what he's done as a creative scientist, research scientist, as a visionary leader of this laboratory, as a leader on the international and national scene, as a statesman for science policy, and more recently, since his retirement in 1999, as the director of SLAC, after serving for 15 years. He's now become quickly an influential and honored contributor and leader in the study and analysis of energy and climate issues. Now, I could go on and spend a whole hour telling you in some detail what those words mean, what he did both in creating a new field of science for which he received the 1976 Nobel Prize in physics, what he did in accelerator developments that made it possible for new fields of research to open up at this laboratory for others to get their recognition and Nobel Prizes, and what he did in energy and climate studies. In fact, his first book in that subject was honored as the Science Book of the Year by Phi Beta Kappa. And go on, but you didn't come to hear this. You came to tell him, to hear him tell you about the science. So you have to read in some way the details to get some ideas of what the depth and breadth of his contributions have been. To make the scientific history, the frontier of SLAC, in fact, to make it possible for SLAC to be on the frontier for 50 years. Let me just make two short personal comments. Bert and I were both members of a caravan across the country in 1956, coming to Stanford. That was a year when, for some reason, having to do with what was going on in the high energy lab, where a 200-foot machine was the progenitor of this 10,000-foot machine out here, and work headed by Pete Panofsky and Bob Hofstadter. 6 of us that I know of all came out from MIT, all within a 1-month period. I had been here as an instructor for 2 years, but I came running back when they invited me to come permanently because I had seen the future coming along. Bert came back to be a postdoc with Panofsky. Henry Kendall came back to be a postdoc with Bob Hofstadter. A couple others came. A graduate student came it was my great privilege to have him be my graduate student, that I could be his supervisor. So it was really an extraordinary invasion in summer of ¡56, which had a big impact on both places. Of course, we say Stanford was the winner. I don't know what the East Coast says. The other comment is that Bert also had a very high percentage winning record in the annual softball game that we had here. There was a reason. It wasn't Bert. It was that the theorists were playing experimentalists. And the theorists were all very good cricketers and soccer players, but they'd never played baseball. And so I had the losing record and he had the winning record. But anyway, let Bert speak for himself.
Sidney always makes excuses for baseball. He refuses to acknowledge that I was the pitcher for the experimenters. There are really 3 stories that go on about SLAC, and I'm only going to tell you one of them. The 2 that you're not going to hear about from me are the intrigues between the university and Washington in establishing a laboratory here, and the arguments within the university about taking on what was the biggest science project in the history of the country for civilian purposes. Of course, there had been the bomb program, but SLAC was the first $100 million conventional civilian science program, and there were lots of discussions at the university about whether they were getting in over their head or not. That all started in 1956 when I arrived, but I arrived as a postdoc, and I was not involved in any of that stuff. So you're not going to hear it from me. There are people around who can tell you all about it, but they're slowly vanishing, and I don't know what's in the university archive. So what I'm going to do is going to give you a scientific history. I'm going to give you about a year a minute here. So I can't really cover this in details. I'm going to hit the high spots. There are literally thousands of scientific publications that have come out of the work at this laboratory. And let me start off and tell you a bit about where it comes from. This is supposed to work, but it doesn't. So I have to ask one of the experts what to do here. Is it too far away?
There you got it.
All right, what's the secret?
Just that one, that's all I did. You probably just needed to sync up.
All right, okay. So here's a picture of the lab as it looks today. You don't see a lot of accelerators. What you see is this long above ground building. That's not the accelerator. The business parts are all underground. You see a few surface facilities. So the lab today is very different from what the lab was 50 years ago, because if you try and do the same thing in science for 50 years, you're guaranteed to become obsolete. Science evolves and laboratories have to evolve with them, if they are going to remain on the frontier. And SLAC has changed. The program has elements that were the same as, that are the same as the early elements. We've got other programs that nobody even thought about way back then. We started in high energy physics. That was the justification for building it. But in parallel with high energy physics came a whole program in what we call here photon sciences, and that too has become a main line, and in fact, at this moment is probably the largest part of the laboratory. It all started with this. This is the old accelerator that Sid mentioned. This is the high energy physics lab where there was a machine that produced 700 million electron volts of energy when I arrived and slowly crept up to 1 billion volts of energy. This is where Robert Hofstadter did the research that ended up getting him the Nobel Prize in 1961. But even before the prize, there were thoughts about a much bigger adventure. And here are the 4 co-conspirators who are responsible for the proposal to build SLAC. The first meeting of that group happened in 1956. And the 4 of them are, let me see if I can get my laser pointer running here. It's weak and feeble. Is yours stronger and better? Yeah. Okay. But which button is that? Is that the red one? Okay. That's Panofsky. That's Bob Hofstadter. That's Leonard Schiff, the chairman of the department. And that's Felix Bloch, the first Nobel laureate at the Stanford Physics Department. And between the 4 of them, they were already thinking of how to take the work that was being done by both Hofstadter and Panofsky and extrapolate it up to much higher energy. The first proposal for this machine went to Washington in 1957. The Eisenhower administration announced its support in 1959. The contract with the Stanford trustees was signed in 1962, and the first beam came on in 1966. That's the good old days. You can't do anything with Washington and our government with that speed. That's sort of like going faster than today's current speed of light. It takes money, more reviews, and all sorts of things. But back then, you could do things relatively rapidly, and it was done relatively rapidly. That's the accelerator. It's actually 25 feet underground. The big thing here is actually the support tube, and the little thing up there, that's the business part. There's a hole in that accelerator that's about this big around, and that tube is 2 miles long, and this very intense beam of particles has to be guided from one end to the other, and that was a very impressive job. Setting it up was, to the trustees, something of a risk. It wasn't the standard university program. SLAC is not part of Stanford University administratively. SLAC is what's called a government-owned, contractor-operated facility. This was a system set up by the Atomic Energy Commission right after the Second World War, when they knew they needed more laboratories, they wanted to support more science, and they knew perfectly well that in Washington they couldn't have the breadth of talent that was needed to do the job that wanted to be done, not just on weapons, but on the science programs that were going to be needed to support the development of a broad national program. So government-owned, contractor-operated means that the brains are out in the field. The administration and the decision-making on what programs are done is in Washington. And Stanford University runs the program and is responsible for making sure that the staff is good and the program is done well. What I say when I talk about what it means here is that the people in the GOCO laboratories tell the government what could be done, and the government sort of picks from the menu and said, these are the most important things that should be done, and then they supply the funds to do it. There was a major culture shock for the university in establishing SLAC, and that culture shock had to do with something that we called users. If you look at the university and you look at the facilities of the university and the institutes and what have you, those are things for the Stanford faculty. The high-energy physics lab, the father of this thing, was a Stanford facility. But a $100 million project, that had to be a national facility. And being a national facility meant that Stanford had to open this up and run it in a fashion that would say the best science would be done. So part of the original contract was the establishment of 2 committees. One called the Program Committee, 12 members, no more than 2 from SLAC, that would select from proposals to use the facilities that were submitted from any place in the country, indeed from any place in the world. And the other was something called the Scientific Policy Committee, which would report through the president of the university to the Atomic Energy Commission, now the Department of Energy, on how well it was done. Well, that was quite a change in the way things are done in a university, and it had some interesting ramifications, and part of the story on the arguments about establishing SLAC that I wasn't really privy to are that story. The archivist knows that story. All those people kept good notes, but I don't know that story, and I'm not going to tell you about it. So Here are the lines of accelerators at the laboratory, and these lines define the programs. This is the high energy physics line, and off from the high energy physics line comes what we now call photon sciences. And what I'm going to do is I'm going to run you through the highlights of this one first, and then I'm going to tell you back over and run you through the highlights of this one, and I'm going to end up with some other ones which aren't even on that thing. So both of those lines have created new opportunities and were first more often than they were seconds. Outside Stanford users, remember the users, the different thing about this at a university, went from about 100 when SLAC first turned on, to 3,000 when I stepped down as director in 1999. And I think they're still sitting at something between 3,000 and 3,500 because there's only a limited amount of time on these accelerators for people, and it can't keep going up. In the 10 years starting in 1967, experiments with the LINAC and with the Spear storage ring, which I'll tell you about, changed high energy physics and began to change photon science as well. This is what the lab looked like in 1967 when it first came on. The major facilities were hidden in these two buildings. There's nothing in those two buildings that goes on in the experimental program. There is some research support and accelerator development that goes on there, and the whole program is totally different today than what it was then. But let me start off with the first of the major programs. These are things called spectrometer magnets. They're all pointing at a common point over here, which is where a target would be, where the high energy electron beam would smash in to a target, and then these spectrometers would take the secondaries that came off them, analyze them, and get some physics out of it. Why 3? It has to do with kinematics. If you think, I don't know, everybody here is old enough to have gone bowling or something, and you know perfectly well if you bowl at the pins and you go only a small angle, you take very little energy out of the bowling ball. That's for the big one. But the maximum energy you can get at bigger angles is not the same. And so this one, although it looks bigger in this projection, is actually only a third as long as that one. And hidden over here is a still smaller one, which for back angles had still lower energy. So what to do with these? Well, the first experiments were pretty clear. After all, the justification to build this had to do with the program that Bob Hofstadter had run at the High Energy Physics Lab. And after all, Bob's Nobel Prize came along in 1961, so it's pretty clear what the first experiments were going to be. I was on the first program committee, and the first proposal to work in here actually proposed doing something different. The proposal committee said, no, you go do what this is built for, and then you do the other thing. But fortunately, the group that was doing the experiments had the attitude that once they were approved, the time was theirs. And they went ahead and made the first revolution in particle physics. Now, this is a very simple curve, but if you look at it, everything falls on top of each other. But the energies of the particles and the angles that they come off the beamline are all different. So how come all of this can lie on top of each other? Well, the way they can is this is cooked up with a different set of kinematic variables, and those kinematic variables show something that came to be called scaling. There was something going on there that said if you took the right ratios of angles and energies, you get the same answers. The program from those experiments showed something that nobody had ever known before. we had a model of how the elementary particles were built, how the proton was constructed. The proton was supposed to be constructed of smaller entities called quarks. But back in those days, the quarks were thought of more as a cataloging mechanism rather than as real entities. This showed that they were real things inside the so-called elementary particle. And I remember when Sidrell said, there are seeds in the grapes. That's what it's showing. There are seeds in the grapes. The quarks were not mathematical fictions. The quarks were real, and there was a substructure to the elementary particles. That was the first of the revolutions that came along, and all of a sudden, what was a cataloging system now became the foundations of the structure of matter, of all the protons, all the neutrons, all the things that make up helium and the sun and you and me and all the rest of that. That now suddenly became real. Then came the second thing, which is colliding beams. I talked to you about bowling. Okay, I'll talk to you about bowling again. If you think of a big, heavy thing coming along and hitting the bowling pins, the pins fly all over the place. Very little energy comes out of the bowling ball. It just goes on crashing into the backstop. Now think of an alternative. Suppose instead of that, I could roll two bowling balls at each other, and that pin right between them would be squashed and turned to kindling when they hit. Colliding beams is to do that. Instead of taking a very high energy particle at something at rest, you take two high energy particles and collide with each other. Now, any of you who know anything about the special theory of relativity can get all the equations. The available energy, if you're in the fixed target, goes up as the square root of the energy of the incident beam. But if it's colliding beams, it goes up linearly. So you don't have to go too far before you have a lot more energy from the colliding beams. This was built with modules. What you see here is one of the modules that got moved in to the storage ring. Underneath this shielding is a ring of those modules, experiments here and experiments here. And since this is a historical society, I can tell you that this was the last wooden trestle bridge built in California. I think in their last modification, they made the terrible mistake of replacing it with steel and concrete, so it's no longer there. So underneath that is the shielding blocks, and also inside one of those was something else that's completely new. The first of what has come to be called hermetic detectors surround the interaction region completely. Look at everything that comes off in these collisions. Because when you collide these particles together, my picture has always been, it's mine too, so I can say it even though some of the theorists will laugh at me. I always figured that these particles come together, created a tiny micro fireball, and from that fireball could be born all sorts of other particles. And those all sorts of particles only had to obey certain constraints. The total energy couldn't be more than what came in, and the momentum had to be balanced, and angular momentum had to be balanced. But anyway, you could do a whole bunch of things. And this facility actually got proposed first time in 1964. And we had a very interesting situation. The theorists in particle physics were all for it. They thought it was terrific. The experimenters thought that this was an odd corner because most of the experimenters worked on proton machines, not on electron machines. And it took from 64 to 70 to get approval to build the storage ring. It only took 2 years to construct it, from 70 to 72. The detector was ready in the fall, and by 74 came this. Now, doesn't look like much, but if you look at the scale here, and these are all logarithmic, the widths of these curves are about 1 part in 100,000 of the energy at which they occur. All the things that we thought about high energy physics said that this was not possible. We had the old quark model, the experiment of inelastic scattering showed that the quarks were real, and that model did not allow anything like this to occur. There were other unstable particles. Until this moment, no one had ever seen a particle which didn't fit into the original quark model. This was the first one that was not allowed. Now, the thing that made such an enormous impact on particle physics was in the same issue of the Physical Review Letters was published a paper by another experimental group working on the east coast of the United States that found the same effect. So back-to-back papers, same PhysRev letters, instant confirmation, and with that instant confirmation came the notion that the quark model had to be modified, and modified it was. There was another experiment. This was 74. The other experiment was in 75. And the experiment in 75 showed something also that wasn't supposed to be there. It showed that there had to be more than anybody thought. And I'll come to that in a second. So, what do we have? What we had in 1974 was a quark model. These are all the fundamental elements, U, D, S, the quarks. These are neutrinos and electrons and muons, and there was no relation between them. We just knew that this was real. Okay, so we knew that was real from the experiments done by Taylor, Friedman, and Kendall. That was a Nobel Prize in 1990. It took a long time for that one to come. I never really understood why so long, but it did. Then came the colliding beam experiment. My assistant's really very good with this PowerPoint stuff. I couldn't fly anything in like that. So instead of all those unrelated things, there were families, and the quarks were in families, and those families were related to the leptons, and all of a sudden there's now some coherence to it. And then in 1976, I had the opportunity to meet the King of Sweden. You notice I was taller and thinner. As you get older, your discs shrink, but maybe your mass doesn't, and so you have to get wider. Well, the next thing in 1975 was Martin Pearl's finding something that also wasn't supposed to be there. These are new leptons, like these and these, but still heavier. And according to the new standard model, with that, there had to be more quarks. It took another couple of years before the first of them, this one, was found at Fermilab, and then it took decades until this one was found too. But the standard model now includes all of these as the basic building blocks of all of matter, and Martin Pearl in 1995 got the Nobel Prize for that too. So we have a new standard model now. The standard model has these three families, and the standard model of today has the same difficulty the old standard model before SLAC came on had. And that difficulty is that if you extrapolate to very high energy, you get ridiculous results. You get probabilities of reactions that are bigger than one. It can't be. And people have been struggling ever since the 1970s to find what lies beyond the new version of the standard model. And everybody's hoping now that this new giant machine in Europe called the Large Hadron Collider, LHC, is going to tell us. Well, things go on, and at SLAC, we went to a bigger colliding beam storage ring. This time as a partnership between SLAC and Lawrence Berkeley Laboratory. So SLAC and Lawrence Berkeley Laboratory worked together on developing that machine. It began its research in 1981 and continued until its later replacement, and I'll come back to what it was replaced with. But the colliding beam story keeps on. The question was, what was going to come after this PEP-sized machine? And designed for a colliding beam storage ring that reached 100 billion electron volts in energy was made, and it was actually built at the CERN laboratory in Europe. I tried, and the person who headed the Scientific Users Organization in Europe tried to get this done as a joint US-European project. Didn't work. The Europeans didn't want it. The Americans didn't want it. But then came a problem. What were you going to do for an encore after that? So if you wanted to go up up by a factor of 10 over that machine called LEP, Large Electron Positron, the CERN people in Europe like large as the leading element, you have to go up like the square of the energy. And that's how big an accelerator would have to be to go to 10 times that size. Now, it's kind of nice that you can have one collision point in London and another one in Geneva, but this, while not scientifically impossible, is financially impossible. So what was going to happen? Well, what was going to happen was the development of something new called a linear collider. Instead of going around in a circle, collide them head on. Why? Well, the things that made photon science so good here were because the X-rays that are spun off when you bend particles in a circle. You didn't have those X-rays. So instead of going to that huge diameter to keep the X-rays down, you could go to very big linear accelerators, collide them head on, and have a much smaller and affordable machine. So this idea came from a meeting at which someone from Cornell, someone from Novosibirsk in Russia, and I got together and discovered we'd all been worrying about the same problem. And we had the linear collider. Now, how are we going to do this? Well, we cheated. We bent it. And you can do that as long as the energy is not too big. So in this one, both electrons and positrons come down at the same time, and one goes one way and one goes the other way, and they collide in the middle. That machine began operating in 1988, and it set the stage for a big study internationally now of what's going on to build actually a big one. It hasn't been built yet. The last in the line of the high energy machines is called the B factory, and it's actually a 2-ring machine. This is the highest intensity machine that had been built. It produced an enormous amount of physics in its unfortunately short career, and the financial crash and the budget problems of 2008 forced it shut down in 2009. It should still be doing good things, but it's too bad that we couldn't convince the Gov to keep going. I now want to switch over to the other line. And I'm going to switch over to the other line, and I'm going to go back in time now, the X-ray line. This began as a spin-off from the high energy physics program. And the parents of this one are these 4. Seb Doniak of applied physics, Bill Spicer of electrical engineering, Jerry Fisher, accelerator physicist from SLAC, and Ed Garwin, condensed matter physicist from SLAC. Doniak and Spicer came up with the notion that if one could let the X-rays out of the storage ring. Remember, I told you one of the problems was when you bend electrons in a circle, they emit X-rays. You would have an X-ray source that was 1,000,000 times the intensity of the best X-ray tube you could buy. And with that, they said, you can revolutionize condensed matter physics. Well, that was not my bag, condensed matter physics. So I had two questions. One, can we build it? Can we do it? That was Fisher's. And Garwin's question was, were they blowing smoke or not? Garwin came back and said they weren't blowing smoke. Fisher came back and said, yes, we can do it. It isn't easy, but it's worth doing. And so, in a simpler life, it was done. It doesn't look like much, but that is the first vacuum chamber to let the X-rays out. Notice it's bent. That's bent to go around the circle in the storage ring, but it's got a tangent port on it to let the X-rays that are emitted in the forward direction as you bend out to get used. It turned out that Doniak and Spicer didn't know the half of it. In fact, they didn't know the 20% of it. It delivered its revolution in condensed matter physics, in biology, in some medical things, in geophysics, and environmental studies, and it was really quite something. I'm just going to mention a few of the things that were done. This was a very unexpected application. It doesn't mean a thing. I just put it there to remind me of what to tell you. This is an application in what came to be called structural biology. Could you use these X-rays to find through diffraction patterns, could you find the structure of biologically complex and important molecules? And the answer was yes, you could. Keith Hodgson, a professor of chemistry, decided that this was going to be his bag. And why a chemist decided that he was going to find the structure of biologically important molecules, you have to ask Keith, but he did it. And this became a very big deal. And in fact, later on, when we made a big upgrade to the machine, it was such a big deal that the National Institutes of Health paid half the cost of the upgrade just to have that, and you will find structural biology beamlines all over the place. The photon science program on the Spear storage ring started off parasitic. It was just that line was tangent to the beam, and whichever way the storage ring was operating for high energy physics, those are the X-rays that they got. Later on, it became half dedicated. The storage ring high energy physics program was slowing down, and the synchrotron radiation program was speeding up with all these other unexpected applications. And in 1982, half the running time was turned over to the synchrotron radiation program, and they could set the conditions of the machine. And a further upgrade in 1992 led to its own injector, what have you. But in 1988, that's this picture, the whole Spear storage ring became dedicated solely to the synchrotron photon science program. And here I'm handing to Artie Bienenstock, who was the director of it, my virtual key to the machine, and they certainly did it. Another rebuild was done in 2004, And the spear storage ring is something like the Cheshire cat. It's not that the only thing left is the smile. The only thing left is the shielding blocks you saw that went over the magnets. Everything underneath is replaced again. Lots of things came out of it. Again, I don't intend to tell you what that's about. That's to remind me. That's one of the other major discoveries. That has to do with high-temperature superconductivity and how it worked. How high-temperature superconductivity worked was a big mystery for a very long time because it didn't work the same way as the conventional superconductivity, which required liquid helium and all the rest of that, didn't work that way at all. And it ended up getting all sorts of awards and getting all sorts of prizes for people. One of the Stanford faculty had the notion of adapting this for environmental science. And the environmental issues that it started off with were identifying trace elements and their valence states. I don't know how many of you remember that movie about, which I remembered its name, the one about chromium-4 and chromium-6. One's a carcinogen, one isn't. And there was a pollution question and what have you. Question was which. Come on, one of you must remember the name of that movie. Aaron Brockovich, right. Well, what you could do with the storage ring and environmental sciences is you could do analyses at sensitivity levels that were orders of magnitude lower than you could do with ordinary chemistry, so it became very good too. And here is another one, RNA polymerase II. This is the mechanism that's used to translate genetic information in DNA into the proteins that are needed to build cells that make them work. And this was the next Nobel Prize for SLAC. And that's Roger Kornberg with the Chemistry Prize for 2006. And we'll think that there are lots more chances coming along. The latest thing in the photon science is what's called the free electron laser. Now what you're doing is you're using 1/3 of the LINAC and a series of magnets that wiggle the beam back and forth by little bits to generate coherent X-rays of an intensity that's even more unprecedented. There's a picture in the undulator hall that shows you the magnets that generate this gentle little wiggle back and forth going off into the distance. There are a lot of them. That was built, and within 2 hours of turn on, it was producing X-ray laser light. SLAC's got a very good reputation at building things. The B factory, for example, exceeded its design luminosity within 3 months of turning on. All the other things were on time and on budget. And this is now our pride and joy. This is the world's leading facility for advanced synchrotron radiation work. There's a lot to do with the storage ring, but the frontier stuff is for machines like this, and this is the first of them. And so SLAC is now #1 in the world in this area, and it will keep on being #1 in the world if people are nimble enough and thoughtful enough about where we're going. The improvement, phase 2 of this machine is already improved by the Department of Energy, and I think construction will start soon. So what makes this so productive? Well, what's been going on here is here's the X-ray tubes. You went first to the bending magnets for synchrotron light. You got about 1 million times the intensity. Then you went to these undulators, shorter ones than this. You got another 1 million times the intensity. Then you went to the X-ray laser, and you got still another 1,000,000 times intensity, but this time you got monochromatic X-rays and X-rays in a very tight bundle, and you do things nobody can think about. If you want to compare it over here, you can see what's been happening to the productivity of these compared to Moore's law. So if I look at, had we followed Moore's law, what would we be like? Well, we would be 10 orders of magnitude lower in the power of these facilities than they actually are. Now, there's lots going on here now that's not based on accelerators. And here is SLAC's first venture into space. This is an Atlas IV rocket lifting, and up in here is a device that was designed to measure high energy gamma rays coming from space. We had to convince NASA that this was a good thing for NASA to do. We had to convince the Department of Energy that it was a good thing for the Department of Energy to invest in. And I'll tell you, NASA was a lot easier to convince than the DOE. Another thing about this was that NASA had never done an international collaboration except by government-to-government agreements. And we persuaded them that they should do this one like high energy physics with a laboratory-to-laboratory agreement. They finally agreed to do that. And so there was nothing that said these governments would honor their commitments. And we had the usual problems. One government pulled out. We had to get somebody else to pick up the slack. They picked up the slack. It got done on time. And it's riding off in space. Right now, it's up there. And it is doing a terrific job. I don't know how many of you are in the science business, but you know if you make the cover of Science magazine, you are a very big deal in science. And this one has made the cover of Science magazine, and there are lots of things about X-ray blazers and gamma ray sources and what have you. It's still going on. It was an international collaboration. What's a laboratory SLAC doing in space? Well, what SLAC had was the technology to detect these gamma rays, not only to detect them, but to tell exactly what direction they were coming in, and the computer technology to analyze them. And in fact, the operations center for that facility is here. It's over in the other building. We don't run the spacecraft, but all the data comes down to the ground here to be cataloged. There's another nice thing about NASA. I think we should adopt it in high energy physics. With NASA projects like this, you have to put the data in the public library within 6 months of getting it. So the consortium that built it gets 6 months to look at it. But after that, everything goes in the public library. Anybody, Sandy Dornbush, can decide he wants to get hold of some satellite data on high energy gamma rays and start writing the sociology of gamma ray emissions. And he can do it. It's all available. So it's been up there for 4 years. It's got its next 2-year extension, and it'll probably get extended for 4 or 5 more years. It's interesting. It doesn't have any disposables for fuel. It's pretty cute the way it's done. So what's going on now? Lots of things are going on now. In the advanced accelerator field, people are looking at how to get a lot more bang for the buck. If you look at the linear accelerator, you can gain energy at 20 million volts per meter of length. This is an advanced accelerator that gets you not 20 million, but it gets you 20 billion volts per meter of length. Now, can you turn this into something practical where you got good energy spectra and good collimated beams? That's what people are working now. There's a large program, well, not large enough, in fact, but there is a significant program in the United States looking at these advanced accelerator programs. I would say SLAC's is the biggest one. There's another program in Lawrence Berkeley Lab and still another one in Brookhaven, and we're going cruising along. So I want to leave some time for questions, so let me just conclude with 2 slides. What's going on now? SLAC is beginning to move toward doing more that doesn't involve the accelerators. So it's taking a move toward energy. And there are 2 joint SLAC Stanford institutes. Remember what I told you about government-owned, contractor-operated. Just because Stanford operates it doesn't mean Stanford owns it, and it doesn't. So these are joint institutes between Stanford and SLAC, and each of them puts money into it. And the first one, SIMES, is the Stanford Institute for Materials and Energy Sciences. And SUNCAT is the study of catalysis, looking for direct ways, for example, to produce hydrogen from sunlight into something or other with an appropriate catalysis. There's lots of non-accelerator experiments going on underground to look at some of the properties of the beta decay program in nuclear physics. LSST, this is a #1 priority in the decadal survey for ground-based astronomy. It's the Large Synoptic Survey Telescope, and SLAC has the leading role in developing the camera. How come? Well, the camera's got 3 billion pixels. Think of your digital camera. That's not such a big deal because SLAC's already built detectors with 300 million pixels. So this is a case where the technology is taking us along. I said we are the world's leader in X-ray sciences. The upgrade is approved. The satellite's working. Advanced accelerator work is ongoing. And the future, well, that's up to the present inmates at SLAC. It's up to the faculty at Stanford, and it's up to the users. Present program is going to keep SLAC on the frontier and among the world leaders till 2025. That's roughly 15 years. The missions of national laboratories are large-scale, multidisciplinary problems of importance, and it's up to the new director. We're getting a new one coming in. The selection's going on now. The faculties and the users to be thinking about what are the next big things. 50 years from now, on SLAC's 100th anniversary, I hope somebody will be giving a talk on what kept SLAC on the frontier for its second half-century. It takes a long time to bring these new things about. And since we've been doing it for 50 years, I have great confidence that we'll continue to do it for a while longer. Thank you all. What do you want to do about questions? You want to run the Q&A?
They have to use the mics in the aisles because it's being recorded.
Okay, there are microphones in the aisles. If you want to ask a question, hold up a hand and someone will bring it to you. Don't ask questions that are too difficult, however. And also, please do ask some. I think they all want a drink.
Yeah, you talked about the special arrangement.
Sorry?
You talked about the special arrangement between Stanford and SLAC. How did that differ from the arrangement between the University of Chicago and the Fermi? How is it different from some of those previous labs?
The University of Chicago and the Fermi relation is evolving toward ours. The thing that was really different about SLAC was while administratively separate, SLAC was academically integrated with the university from its birth. So SLAC actually has 2 faculties. The director of SLAC also functions as a dean, and the SLAC faculty goes through the same kind of appointment procedures with all the searches and the references and the advisory board and all the rest of it. That's been going on since the place opened its doors in '63. So academically, the lab reports to the provost. Administratively, it reports to the president. SLAC was the only laboratory like that until the Fermi National Accelerator Lab outside of Chicago, till its contract was modified, I think only 3 or 4 years ago, to give the University of Chicago the same sort of relation with Fermilab as the relation between Stanford and SLAC. All the rest of them, they have senior scientists, they have people from universities who spend a lot of time there. Lawrence Berkeley Laboratory has people who are professors at UC Berkeley who work and run groups at Lawrence Berkeley Lab, but they're not integrated. They're separate academically.
What's the status of the International Linear Collider, and what's SLAC's role in its development?
Well, unfortunately, for reasons that I cannot fathom, the International Linear Collider, when it came to the choice of technologies, picked the one that didn't work and rejected the one that did work. And so it's been focused on superconducting RF ever since. It's actually an international program, SLAC's part of it, but when push came to shove in developing a machine, it turned out to be much too expensive. The target was 500 GeV, half a trillion electron volts collision. You got to remember that the Large Hadron Collider is running at 8 trillion volts and is supposed to go up to 14 trillion. So this thing, when you turned it into US accounting, would have cost $16 billion for something of, let me call it a non-competitive energy. Had the International Linear Collider gone much faster, you could have made the scientific case for turning it on about now, but it was impossible to beat the financial problem of something that expensive. So things that are going on now are people are looking at alternative technologies. It's still international, it's still a coordinated program, and we'll see what people come up with that will let them build a more affordable machine at a higher and more appropriate energy given what's already going on in the proton world. That's one that we'll have to wait and see.
This is a bit of a mundane question, but if we have a big earthquake on the San Andreas Fault, is SLAC going to be okay?
Well, we had one not that long ago, and I can tell you exactly where I was. I was at the men's room on the 3rd floor, and it's very hard to maintain your aim when the building is shaking. We had somebody down in the tunnel underground at the time of that earthquake, and he told me he could see the bulge in the wall coming down this 2-mile tunnel toward him, and it passed right by, and we had to realign the linear accelerator. It took us 3 days to get it back operating. The round machines took much longer because the alignment is more difficult. Underground is about the best place to be in an earthquake, unless the fault runs right through you so that you get sheared and cut off. But there wasn't any problem. And if you look at underground structures, what happens is the Earth moves as a body and comes back. And if you look at buildings, what happens is the bottom shakes and the bottom makes the tops whip, and that's what knocks buildings down. So being underground's a good place in an earthquake, and I sure hope I don't have to go through another one on the 3rd floor.
I wondered, you spoke of arc bending, and I just wondered, is there a loss of energy as you go around the curve?
Yes, you emit X-rays, and one of the big problems in these circular storage rings for electrons is putting the energy back in to keep them going. That's why when they go up in energy, they have to go up a lot faster in diameter, because to keep the minimum cost, the radius has to go up like the square of the energy. So if I go up 10 times in energy, I got to go up 100 times in radius. So the CERN machine, the largest electron-positron collider ever built, was 27 kilometers around, and the picture I showed you with London and such is 2,700 kilometers around. Now, the proton colliders don't emit so much synchrotron light. They emit enough to give a lot of problems because they have to run on superconducting magnets, and you don't need a lot of energy to disrupt the superconductivity. But yes, all that X-ray stuff that's spewed off by those electrons, that's the plague of high-energy physics and the pleasure of photon science.
So I think we have time for one more question up here to the right.
Okay. Earlier in your talk, you said that the standard model runs into problems as you get to much higher energies, problems like probabilities greater than 1. Could you say more about, what current research is doing to better understand that phenomenon or that problem?
They're waiting for experimenters to tell them what's really going on. The theorists have been struggling with this since the late 1970s. And the hope has been with each new generation of accelerators, you would find the clues, just as we found the clues in the 1970s to the problems with the first version of the standard model. The trouble is there haven't been any answers. The standard model is perfectly fine, and what's called new physics has not turned up. So you can look in the journals and you will find thousands of theoretical papers proposing things to fix this problem, and the energy of the machines goes up, and most of the thousands get thrown away, and new proposals come along. I don't know if you remember the ill-fated SSC, the superconducting machine that was supposed to go in Texas. It was eventually killed for a combination of political and technical reasons, but it was designed with what was called then the no-lose theorem. It was sufficiently high in energy so that you had to find the problem, or the whole foundation of physics would fall apart. But it never got built, and now the Large Hadron Collider, the CERN machine, is, when it gets up to full operation, will be a third the energy of the SSC. So if we're fortunate, that's going to be enough to give the experimental clue as to what's going on. When we did the colliding beam experiments at Spear here, and we showed that this particle was there which wasn't supposed to be there, we did that in a climate where there are all sorts of papers saying what the way out of the dilemma was. The experiments of SLAC plus 1 done in Europe pruned that tree, and all except one explanation were shown to be wrong. And that was the new standard model. That's the one we're living with. That's the one where we now know if I go high enough in energy, I'm going to be in trouble. And that's where we're looking for the experimental clue that tells us what's the way out of the trouble.
So at LHC, you hear a lot about the Higgs boson, you hear some about supersymmetry. Are you talking about something completely different and unexpected?
No, Higgs boson is needed, but there's supersymmetry. There are all sorts of other possibilities besides supersymmetry. The supersymmetry guys are the best propagandists in the business. It's the most popular explanation, but there are others, and we'll see.
Well, on behalf of the Board of the Historical Society and Charlie, I want to obviously thank our members and our visitors today. And as well, thank you to Sidney Drell and, of course, to Burton Richter for taking us on this wonderful journey. And please join us outside for a reception.